So I can start with a little summary of the key points up till now. Again, those are good sort of study points or a good place to start to sort of check that you understood the material of the previous lecture. And then we'll continue with our dynamics of fluid motion. And basically we've derived the most important equation, the Navier-Stokes equation. That's what we just did, excuse me. And then we can apply that to derive new equations from it, the energy equation, the Bernoulli equation, the momentum equation, and Euler's theorem is another name for the momentum equation. And we're going to look at those in two applications, one for the Euler equation to find the force exerted on a something, a grill or a grate that's like embedded in a flow. And then we're also going to see an application of Bernoulli's equation. And then we put the two together to derive Betz's law, which is that law that I mentioned at the start, which is kind of our motivating thing. Jean-Yves told me that's the most important thing. So then I made sure, I sort of worked back from there to make sure we had all the elements so that we could derive that law. Okay. Oh, okay. Okay, so maybe I'll email that as you're telling me your question.
So ways of solution of putting the energy. Which is the one that we
yeah, so I'll have a look at what you mean, or maybe I can do it from here. So when you're mentioning the numbers, do you mean from this file, the one we just had up? Yeah. And so what were the numbers again?
So I think the first version of equation is 31. 31? Yeah. So that's the general Navier-Stokes equation, right?
No, I would not call that the Navier-Stokes equation. That's a for one thing, I haven't assumed a Newtonian fluid yet. So this is just a step along the way. Yeah, that's just a step along the way for the derivation. The Navier-Stokes equation is well either 36 or 37. Because, and I say that because this is a differential equation that I could integrate forward in time. And notice so on the left hand side, I have the acceleration of the fluid, but it's involving time derivatives of the velocity. Yeah, I guess you could think of it like if I wanted to solve this in a computer, what would I do? I mean, there'll be better numerical schemes than this, but just to sort of show that this could be done, you could just isolate this on the left-hand side. So move this onto the right-hand side. So that would say that if we have the flow field everywhere at some instant, then we could calculate this term, right? That's just the velocity and then its gradient. And, you know, there's actually 9 terms there, but you could calculate them all from the velocity field. This is the gravity, so that's a constant. And then this term I wouldn't know what to do with, right? Because, well, that's the stress tensor, and I don't know what the stress is unless I specify I'm dealing with a certain type of fluid. Here we've chosen the simplest fluid, the Newtonian fluid. And then that's what allowed us to pass from 35 to 36. And now I just see terms that involve P for pressure, mechanical pressure, and EIJ, the rate of strain, the symmetric part of the rate of strain. But that involves the velocity. So again, if I knew the velocity, I could calculate that EIJ. And I just realized that this is really a big shame that I'm pointing at this thing that I'm not sharing. So I could calculate this term from the velocity. I could calculate the divergence if there is any. It's probably very small. Unless it's a high Mach number flow around, you know, flow around an airplane ring, a supersonic jet or something. Then now you might say, well, you need the pressure. Okay, I haven't gone into how you get the pressure, but you get the pressure from the velocity field as well. Okay, that's actually a difficult step in numerical fluid mechanics. Is the pressure velocity field coupling, and but there's a way to do it, and or there are books written on strategies of doing it, but you know, in principle that can be done. So we can get the pressure from the velocity field. So we'd have all these terms would tell me what the time rate of change of each component of the velocity is at each point in the fluid. So I could advance it forward 1 time step, right? And then that would give me the new velocity field at this new time step. And that new time step might be just 1 second later. In numerical ocean models, it's like several, you know, 10 minutes later or something, but or it might be an hour later, actually, depending on the resolution of the model and what they're resolving. But in principle, you can step forward in time with this, not with equation 35, but with equation 36. So that's the Navier-Stokes equation 36, or you can rewrite it as a more familiar form would be version 37. Okay, so I think I've responded in detail to your question. Was there another question? If not, I'm going to try and share the appropriate screen. Oh, that was a very nice question. Thanks, because that let me explain that in more detail. The problem is if I minimize this window to get it out of the way so that I can share the screen here, then I don't see that thing here. So, okay, so I have to push it aside and then, okay. So I think I'm ready to go, right? I sent my PDF file. And I've answered the question. Okay, so the key points from the last lecture were that the Eulerian
That might be compressible flow.
okay. So the Eulerian description, remember we had two descriptions of fluid motion. We had the Eulerian and the Lagrangian. We use almost exclusively the Eulerian. It allows us to write our velocity components as a function of position. For example, the 3 Cartesian coordinates within our continuous fluid and the time. And so using this index notation or tensor notation, I could write that in this succinct way, being careful to use a different index for I and J here, because otherwise it would look like I'm trying to insist that it had to be the same component here or something, which wouldn't really make sense. We went into the material and Eulerian time derivatives, which was a little bit complicated, but it's really quite fundamental to understand those differences. The sort of, to get right to the heart of the matter, when we have the capital D, we're doing the material time derivative. Think of it conceptually as you're moving. It's the rate of change that you would observe moving with the fluid, but computationally you take the Eulerian time, this material derivative equals the Eulerian time derivative, which is the derivative you get just by taking the partial derivative with respect to time. And then you have to add in this thing we call the advective term, which it's the dot product of the velocity times the gradient of the quantity that you're differentiating. Here I just wrote theta. It could be temperature, salinity concentration, concentration of pollen in the atmosphere, what have you. So you take its gradient and take the dot product with the velocity. When we apply the notion of conservation of mass in this continuum framework, we have the material. We actually found we could write it in several different ways, right? One way was to write the material time derivative of the density equals minus the density times this divergence of the velocity. Careful, when it's the divergence of the velocity, it's the trace of the rate of strain tensor, if you like. It's the sum of the diagonal components here of the velocity derivative, or the gradient of the velocity. So in other words, this index I here on top is the same as the index down below. And so there's a repeated index, so you have to sum over them. So there's 3 terms in this quantity. But I call it the divergence because that's the vector calculus name for that quantity. Here it is here, written in vector notation. So when a flow is incompressible, then it means its divergence is small or approximately equal to 0, which we write like that. And I just explained this subtle scaling here at the start of this class, so I think I can skip that in the summary. And we just derive this Navier-Stokes equations, or the Navier-Stokes equation. So this equation 4 here is the governing equation in Newtonian fluid mechanics. Just maybe a little potential pitfall here that I should mention is that we call it a Newtonian fluid, and it's the equation of it's the Navier-Stokes equations is Newton's second law for a Newtonian fluid, but sort of Newton here is used in two senses. Newton was a busy guy, right? Back in the whatever he was, 17th and 18th century. And so he came up with his laws of motion, but he also, separate from that, he came up with this notion of what we now call a Newtonian fluid. Okay. So don't think that this is because it's Newton's second law or something. I mean, it is Newton's second law, but it's for the special case of a special type of fluid, which has very wide application. It's not, it's the most important type of fluid. Applies to the atmosphere and the ocean. Okay, so let's see how this plays out in applications. First thing we can do, I'm going to use all these things. It's not just for fun. I'm going to use this later today. We're going to be doing energy budgets, and well, we're going to use the energy budget is going to allow us to derive the Bernoulli's equation, which we're going to use to get Betz's law, and then we're going to look at a momentum balance. It's also called, or to arrive at, Euler's theorem, and we're also going to use that together with Bernoulli's equation to get this Betz's law. So it's all important. I guess I do go back. Sometimes I don't need the choice of the viscosity, so I will go back to this equation from time to time. Yeah, but this is exceptional. In the most of your work in fluid mechanics, you're going to use the Navier-Stokes equations much more often than this equation 5. Equation 5 is much more general because I haven't said anything about the stress tensor yet. But to obtain, so this is a momentum equation, right? It expresses the in particle physics terms, it's the forces on the right equal the acceleration on the left. But I want to talk about the energy. So to do that, we simply multiply by the velocity on both sides. And a little confession is, it still amazes me to this day that this gives you an independent equation, because we started with just this equation and all we did was multiply by the velocity. But then we get this other equation, which you'll see later that it gives us an independent equation that allows us to resolve this equation for which we didn't have enough information, or we're going to exploit the fact that we have two equations, one coming from momentum and one coming from energy. So we multiply by the velocity, and when I say multiply by, it's important that I use the same index here, the same component of the velocity here. So that means I have to sum over all three components. And so then this will be a scalar quantity on the left and a scalar quantity on the right. as opposed to a vector or a tensor. Or a tensor of rank 0, if you like. But that's what energy is, right? Energy is a scalar quantity. So let's develop the two sides of this equation. So on the left-hand side, I have the velocity times the density times the material derivative of the velocity or the acceleration. I can bring this velocity component inside this material derivative, and excuse me. And then I just have 1/2 the material time derivative of the square product of this velocity component. But then you can look at that and say, well, you know, the 1/2 the velocity squared is the kinetic energy just from classical mechanics, right? That's 1/2 the kinetic, or sorry, it is the kinetic energy per unit mass. So then and we're taking the time derivative. So this is the time rate of change of the kinetic energy per unit mass times rho, the mass per unit volume. So this is giving us the time rate of change of kinetic energy per unit volume. Well, just to be totally careful about that, that would be, you know, assuming the density were constant. So developing the right-hand side, we had 3 terms here, or sorry, it looks like we have 2 terms, but I'm going to expand this stress tensor in terms of the mechanical pressure and then the departures from the isotropic part, or in other words, the part along the diagonal. So there's the diagonal part of this stress tensor, which is the mechanical pressure by definition. And with the minus sign, right, because pressure works in the opposite direction or pushes down pressure gradient. And then if this doesn't ring a bell, just you can look up when I introduced the so-called deviatoric stress tensor, Dij. So this is just a definition of the Dij, is that it's the thing you have to add to minus P along the diagonal such that you get sigma ij. And then conceptually, you should know that the Dij comes from the viscous terms. It comes from viscosity. For an inviscid flow where there was 0 viscosity, or we're approximating it as being inviscid, which we do sometimes, then this Dij would go to 0. Okay, so I'd like to interpret these 3 terms on the right-hand side of equation 8, one at a time. So here's the velocity times the density times the force, the body force, expressed as a force per unit mass. So, well, force per unit mass times mass per unit volume gives force per unit volume. And then this is the velocity in that direction, right? Because they have we're taking the same component of the vector here, the I and the ith component here, and we're summing over those 3 components. So this is, I'd don't know if that's clear, but this is the work done by that body force. In fact, it's the time, it's the rate at which you're doing work with the body force. And so if that needs some explanation, you remember work is when you apply a force through a distance, right? But here I'm multiplying by the velocity. So it's like you're applying a force through a distance per unit time, because the velocity is a movement displacement in space per unit time. So yeah, so if you the force times velocity gives power. It's work per unit time. It has to be a vector product, right? If we did this in vector notation, it would look like this. So it's important that you line up the, x direction of the velocity with the x direction of the force, and similarly for y and j, or y and z, which is why I like the tensor notation, because this is just said explicitly here, right? We have the ui times the fi, and then you sum up over all three of them. Of course, if our body force is gravity, then there's only one component to worry about, and that's vertical displacements. So only vertical displacements. It's only for vertical displacements that gravity is doing work. If I push this along here, I'm not doing work against gravity. There's some resistance, but it's because there's friction on its table. And because we can write, remember we talked about conservative forces, and we said that the gravity was an example of a conservative force, which means that we can write it in terms of the gradient of a potential. We usually put a minus sign. It's the body force is body force per unit mass is minus the gradient of the some scalar, for example, psi. But when it's, in particular, it's the gravitational force, then it's the gravitational potential. Okay, so that's the first term. Second term involves the pressure, and it's it's ui times the derivative with respect to xj of delta pi. Well, that just becomes the when you sum over j and take into account this Kronecker delta is 0, except when I equals j, this becomes the ith derivative of the xith derivative of pressure. Well, remember, minus partial p partial xi was the pressure gradient force in the xi direction. So this is the work done, the rate of work done by the pressure gradient force. And finally, I have the third term, which is the velocity times this divergence of the deviatoric stress tensor, which I said comes from the viscous part. In fact, you can write it as for a Newtonian fluid, I can write the deviatoric stress tensor this way, or the partial xj of the deviatoric stress tensor ij would be written this way, times minus ui. So we have two parts to it. I kind of like this because I thought a lot about how you get rid of energy in a fluid flow, and so I've looked at this term in detail, and you can understand it physically. It has the viscous terms have a local effect of diffusing, or in other words, smearing out the kinetic energy. So there's this that's a Laplacian in vector calculus terms. It's a second derivative of the second spatial derivative of these velocity components, which is a term that you have a similar term in, a diffusion of some passive scalar, or in the temperature flow in a metal plate, for instance. You would have a term like this, which makes the heat diffuse. But here we're diffusing not heat, but momentum. And which, when you multiply by the velocity, gives you a diffusion of kinetic energy. I guess a good question would be just a conceptual question, like where does the energy go if we're dissipating? Ultimately, this term also dissipates kinetic energy. So it provides a sink for the kinetic energy. Where does the energy go? It's not destroyed, it's just converted to a different form of energy. And in fact, the form of the energy becomes thermal energy. In other words, it's energy associated with the random molecular motions. So conceptually, you could say it's a change of length scale of the energy, right? The kinetic energy associated with the flow is energy associated with the motion on length scales much larger than the mean free path. That's what we mean by a velocity in a continuous medium. And when it's dissipated into thermal energy, well, then that means it's been converted to mechanical energy at the mean free path scale. Okay, that's a bit of sort of conceptual detail. Let's look at Bernoulli's equation, which is going to be very useful in solving practical applications. So suppose we have a stationary flow. It's also called a steady flow. And what do I mean by that? I mean that the Eulerian time derivatives of any quantity are equal to 0. It doesn't mean that the velocities are 0. They can be non-zero, but it just means that they don't change with time. So if I sit at a certain point in the fluid, or if I put a probe in and I measure the velocity at some point in the fluid, I get some, in general, non-zero velocity, but that velocity doesn't change with time. If that's the case, then it's a steady flow or a stationary flow. Let's furthermore assume that the fluid is homogeneous. That means the density is constant and the It doesn't have to be homogeneous in terms of other quantities. And I'm sorry, the terminology is a little bit confusing, but you have to just know what people, how people use this language. Homogeneous means the density is constant, not the pressure and not the velocity. The pressure and velocity are sort of dynamic quantities that we're going to solve for. But density is more considered like a, well, it's considered like a parameter because the flow is most likely incompressible. So then we just have one density. So then it just becomes a parameter. And I think that's sort of the origin of this terminology. Anyways, that's what we mean. And I also want to consider an inviscid flow. So that means that when we say inviscid, we mean it has no viscosity. So mathematically, this corresponds to this parameter mu, the dynamic viscosity, and therefore also the nu, the kinematic viscosity, equal to 0. And finally, I'm going to assume that the body force is derived from a potential. So it could be the gravitational potential, for instance. So my force per unit mass will be minus the gradient of some potential, for example, the Earth's gravitational potential. And we'll find in this case that we were able to derive an equation that looks a lot like conservation of energy and particle mechanics. What that comment I made about the stress tensor earlier applies here, that when it's an inviscid fluid, when the viscosity is 0, then the stress tensor is just this mechanical pressure times -1 times the Kronecker delta. In other words, it's just minus P times the identity matrix if you write it in matrix notation. Okay, and because we made the stationary flow approximation, there's no Eulerian time derivative of the velocity. It's just 0. So the only non-zero part is of the Lagrangian or material time derivative of velocity is the advective term. Remember, there was the two parts, the Eulerian and the advective. And so we're saying Eulerian's equal to 0, so we're only left with the advection. So let's put all those simplifications into our Navier-Stokes equations. And we have the following. So this is the body force here, pressure gradient force. There's no viscosity term because it's an inviscid flow, and there's no Eulerian time derivative because it's steady. Otherwise, these are all terms in the Navier-Stokes equation. And now I want to actually exceptionally work in vector notation, because I find it's just easier for Bernoulli's equation, and that's unusual because I really much prefer this. Almost always prefer this notation, except there's this just. Well, you'll see. It's easier in vector notation. So I have to translate this into vector notation, which is easy for these terms, right? This is just the gradient of the pressure and the gradient of this psi, but here I have something a little bit, this advection term is a little bit more complicated. But we did do that in an exercise. We in fact, this was our challenge, was to try and write this in vector notation, and we found that we could do it even though this involved tensors of rank 2 that we don't have in vector notation. We could get around that by immediately taking the dot product with this velocity here. So you have the dot product of this velocity with this gradient operator. Looks like this: u dot del, where del is the gradient thing here, the d by dxj, and then the ui just becomes this vector. So we think of that as being some operator that hits this, some vector calculus operator that hits this thing. If you want to know what does it mean, well, it means this, right? Excuse me. Okay, so why am I using vector notation? Because well, I admit this is not at all obvious, but somebody who had a lot of free time, I guess, worked out this identity that this left-hand side has to equal this right-hand side. And so I haven't told you what omega is. Omega is, it's actually an important dynamical quantity in fluid mechanics, so it's worth giving it a name. It's called the vorticity. And it's the, here's how you calculate it from the velocity field. You take the curl of the velocity field. So I could write that in tensor notation if I wanted, like this, and then I could rewrite this thing in terms of tensor notation. But you know what? I really think this is not very useful, so I'm going to just skip equation 15. And let's just, the important thing is that you know that omega is the curl of the velocity. If you want a physical explanation, it's the rate at which the fluid is spinning about an axis. And I have to tell you which axis. It's the axis, the local axis. So if I want to talk about the vorticity here, it's the rate at which the fluid is spinning about an axis through that point. If I'm talking about the vorticity over here, it's the rate at which the fluid is spinning through an axis over there. So so it's different than angular momentum, but it's somehow related because it's related to a rotational motion. And yeah, and that's its definition. And there's, well, I guess there's a funny factor of 2 that comes in, or maybe it's 1/2, I can't remember, but I think it's twice the rate of rotation through that axis or something. Or maybe it's 1/2, I really don't know. Yeah, so that's all we need to know, is that vorticity is this important quantity. And well, this second term is, I think, easy to interpret intuitively. It's the gradient of the kinetic energy density, right? Anyways, so it's useful to rewrite the, so we started with the Navier-Stokes equations. We made a bunch of approximations, and then we replace the advection term with this thing. And now we can make some observations which will turn out to be useful. So it's convenient to define a scalar field curly H that has units, it turns out it's units of kinetic, or sorry, just energy per unit mass, specific energy. And it's made up of three parts, right? It's the kinetic energy, if it's gravity is the body force, then it's gravitational potential energy here, all per unit mass, right? And yeah, I should, so kinetic energy per unit mass, gravitational potential energy per unit mass, and then the pressure divided by the density. And that's interesting because pressure is energy per unit volume. So pressure energy per unit volume divided by the mass per unit volume is like multiplying by the volume per unit mass. So that gives you an energy associated with pressure per unit mass as well. And so a specific energy. And so what's the energy associated with pressure? Can you give me an idea what that would be? It's the, don't worry about giving it a technical term. I just intuitively, what would it be? Think of what is pressure. Pressure is like moment, you feel a pressure force here on the table because little particles of air are bouncing off it, right? So if you think of the molecular origins of this pressure, it's the random motion of the air molecules in this room, for instance. So this pressure is the kinetic energy of the molecules. That's the, yeah, so it's some kind of internal energy associated with the motion on the molecular level that we've averaged out in our continuum hypothesis or continuum representation. Okay, now we can do some mathematical tricks on this thing and take the gradient of H. So what do we mean by gradient? We mean apply this del operator. And so this was the reason for introducing this curly H in this way, is that when we combine that with combine 16 and 17, we find that the gradient of H has to equal just U cross omega, which, and I admit that's not immediately obvious, but if you work through the vector calculus here, that's what it comes down to. And if you're willing to take me on my word on that, or try and work it out on your own later, then that's useful because we can interpret this. This tells us a lot about the flow. We can interpret it as follows. It says that the gradient, this gradient of curly H is a vector. And that vector has to be perpendicular to u and omega, because that's a property of this cross product here, is that the cross product of two vectors gives you a third vector that's perpendicular to the first two. And what does that mean? Well, that means that the dot product of u grad h equals 0 and the dot product of omega dot grad h equals 0. And what that means, remember, this is a steady flow, so that the you could imagine taking a path through the fluid that's always parallel to the velocity. So that would be a streamline, but it would also be a path line of any particle that is advected through the flow, a passive test particle that flows along with the flow. And but as that particle moved along, it would move in the direction u, the velocity. But the grad h equals 0 in that direction. So in other words, h is not changing along that direction. In other words, h is constant along a streamline. That's I've just sort of tried to physically take apart this first statement here. I've just interpreted this first statement here. What this means is that the h, this curly h quantity, has to be constant along the streamline. Remember, it was a steady flow. That was one of our assumptions. The same thing is true along lines that are always parallel to this vorticity vector. And those, so you can call those lines along which you're always moving parallel to a vorticity vector, and sort of the analog of a streamline, but for the vorticity, we call that a line of vorticity. And so h is constant along those lines too. So it's constant along those two types of lines. So that's nice to know, but it's not the form of Bernoulli's equation that I learned in fluid mechanics. It's this is the most famous version, but this equation 20 follows from assuming the body force. So the body force is gravity. So then our potential psi becomes just minus gz, z being the height in the vertical direction. G is the 9.8 newtons per kilogram. Then we take these equations 17 and 19 and just multiply by the density. So we'd have rho times h equals rho times the kinetic energy density here, and rho times the minus gz here, and then we just have p here, right? Because we multiplied through by p. And but remember, density rho is a constant, and if this h is constant along the streamline, then rho h is going to be a constant along the streamline. And that's what we have here. Sorry, let me just go back to look at the sorry, I think there might be a problem with the sign here because when we replaced psi with minus gz and multiplied by rho, I don't see why I don't get minus here, but then I think I should. This looks like the right answer, right? Just thinking physically what this means. Yeah, so I think I made a mistake earlier here in 17. So don't trust 17, or don't trust the sign here in 17. Let me just interpret this physically and then we'll make sense of it. And I think you'll agree with me that the signs are correct here. So as I say down in the text here, it looks a bit like particle mechanics, right? Remember in particle mechanics, if I was just talking about, I have some particle and I'm throwing it in a gravitational field here, I can say that the kinetic energy plus the gravitational potential energy of this particle are conserved, even as the phone is moving up. If it moves up to its highest point and then stops, and then it has zero kinetic energy, but it has its maximum gravitational potential energy, and then it falls back down, and hopefully I catch it here, and it'll have its lowest potential energy, but it has its greatest kinetic energy as it's speeding down. So that's what this equation is telling us, except it's applied to the case of a continuous fluid, right? So we have the fluid velocity squared over 2 is the kinetic energy per unit mass times mass per unit volume. So this is sort of this kinetic energy per unit volume. This is the gravitational potential energy per unit volume. And then we have this funny pressure term, the mechanical pressure. But remember, that's the energy of the molecular motion per unit volume. So this is an energy per unit volume. And it's constant along a streamline. For the cases, or for the, under the assumptions that we made, right? A steady inviscid flow in a gravitational field. Homogeneous as well, density is constant. So I think I've just explained all this. I've also explained this, that the omega is a measure of rotation on a sort of local level. There are flows which are, this is interesting, which are considered irrotational. If you see, you'll see that term a lot if you look in fluid mechanics. You know, there'll be a chapter on irrotational flow. What they mean is that omega, the vorticity, is constant. Sorry, 0. And then things simplify even more. So I'd like to go back to equation 18 and say the gradient of H is not only perpendicular to these vectors, but when omega is 0 for irrotational flow, then grad h equals 0. So h is just a constant. And therefore, so is rho times h. So this energy quantity, energy per unit volume, including these three components, right? Kinetic energy of the flow, potential energy, and internal pressure energy are all constant throughout the domain when it's irrotational flow. Well, I've gone past 10 minutes past the break time, so I think this is we're due for a break. So let's stop there or pause there.